Okay. So I'm going to continue the magnetic scalar potential method. I want to talk about iterative refinement of those coils. So because you're discretizing with that method, you're going to be left with this residual field. And so to account for this residual field, to correct for it, you could theoretically add more wires on top. Alternatively, you could take the scalar potential from your wires and the scalar potential from your residual field and add them together. And then if you find the windings from that result, your new windings will produce the same result. So an overview of this method is, first we use the magnetic scalar potential to find your initial coil windings. And then from those, we can solve for the residual field and its scalar potential, add them together, and then repeat, where we then create the wires again, find the residual field, and continue until we get a solution that converges. And from then you can export the windings and create the coil. So to solve for the scalar potential, I use a COMSOL model. So build your geometry, put in your background magnetic field. And so we have two studies. The first one will solve actually for the magnetic field from your wires. And then from that, you can get the residual field. And then the next study will then solve for the scalar potential. And you can add those together, and then you can start extracting the windings. And so what you can do is you can either do this in COMSOL and take those windings, but that becomes a problem when these points aren't necessarily ordered, and they might also be from two different curves with the same potential. And so to avoid those problems, I just decided to solve for the contours myself in MATLAB. And so for each surface, I parametrize it, and so it becomes a 2D. And then I do a surface interpolant in MATLAB. And then using the contour 3 function in MATLAB, we can solve these equipotential contours to get the windings. And to get the direction of the current, you can use the cross product between the normal vector and the gradient. And then you can transform those back into 3D. Now, the problem with this, though, they'll often be jagged. And so that can cause problems in many different ways. So when constructing the coil, when you're 3D printing it, might make it more difficult. It could lead to long computation times when finding the corrections, and also inaccurate results. And so the first thing to do to smooth these curves is I check if they're supposed to be straight. Just do a linear least squares regression. And if that's within some tolerance value, then you can replace it with its two endpoints, and then you have your curve. And for the rest, MATLAB has this smoothing spline function. And so that will produce a smooth curve. So to produce these full current loops, then you can specify different geometries. So you could do your full coil, but ideally you want to cut that in half symmetry, a quarter symmetry, or even 1/8 symmetry. Or you could even go less than that in some cases. But what that does is it will reduce your computation time and make it easier to find a solution. And so depending on your symmetry, you can mirror the windings. And then since we have the direction of the current from the original ones, we can then solve for the direction in the mirror curves. And then we can connect them just by the nearest endpoint with the same potential. And actually doing that is how the direction of current is preserved. And so if you look here, you can see this is after a few iterations. You can see, I don't know if you can tell, these lines are mostly straight, but not quite. And these are also a little bit curved over here. And so these are the slight corrections to the original double cosine theta coil, which were straight here. And then these were still curved, but. And so then to calculate the corrections, we can import these curves back into COMSOL. If that curve does not have any sharp corners, you can use interpolation curve. Otherwise, you can use a polygon. Polygons are a bit slower, but you can have those sharp corners. You can add currents in the correct direction and then use that to solve for the scalar potential. Put it back in, take the curves back into COMSOL, and repeat the whole process. And so once the error in your target field and your actual field converge, you can then take those windings and construct the coil. Thank you. And I want to give a special thanks to Chris Crawford and Mark McRae for their work on this project as well. Are there any questions?
That was not very nice and short way of describing, very nice way of iteration on that. So what is exactly the convergence where you aim to? So because it doesn't converge to getting the error to zero, but it converges that it no longer gets any smaller with the iterations of that.
Yeah. So I mean, you're never really going to get your perfect ideal coil that you want. You're always going to have slight discretization effects.
But are you on the volume? Are you minimizing the error, like on the over the volume in some like L2 normetric or the maximum error or what?
Are you asking like the metric used to define the error?
Yeah, like what error metric you're actually defining. So are you trying to optimize now the problems, the low winding density areas that we have usually where discretization goes like kind of bad? Are you minimizing those, or are you minimizing just the overall error?
Okay, yeah. So at least in the cases I was using with the double cosine theta coil, what you want is a uniform field here in the middle. And so the uniformity of the field was that metric.
Okay.
Quick question. What do you mean by discretization?
Turning the continuous problem of a surface current into a discrete problem of wires.
Okay, thanks.
Okay, great. Thank you, Mike.